This video is a continuation of what we've been talking about in class about valence bond theory. So we're going to look at an important concept called bond symmetry. So it turns out that, and this becomes important when we start talking about how valence bond theory treats things that in Lewis structures we called double bonds and triple bonds. So we say that bonds have a symmetry depending on the location of the overlap region with respect to the bond axis. So that sounds kind of complicated, but what it means is really pretty simple. So imagine that we have an atom here, we'll call it some element A, and there's another atom over here, B. And so in the middle of those atoms, right, there's the nucleus. So I'll just draw a little dot here in the middle to indicate the nucleus of the atoms, right? So that's where all the protons and the neutrons are, and the positive charge. And so the line between these, so these atoms might bond, right? So there's an orbital here, and there's an orbital here. They overlap, and they've made a covalent bond. And so the bond axis is just the line that connects the nuclei of the two atoms. So we call that the bond axis. And so we're asking, hey, where is this overlap region? Is it on the axis, or is it arranged above or below or in some other way around that axis? And we call that bond symmetry. Okay? So bond axis is just the line that connects two atoms, and we're just going to look at where the overlap between the orbitals occurs. Okay, so thinking about valence bond theory, we've got overlapping orbitals. Where does that overlap occur? So the first kind of symmetry is called sigma symmetry, and so this little letter here looks like kind of an O with a long flag on one end. That's the lowercase Greek letter sigma. So this is called a sigma bond. And this is when the overlap contains the bond axis. In other words, where the overlap is on the bond axis. So this picture that I've drawn up here has the overlap shish kebabbed by that bond axis, and we would call this a sigma bond. So this right here is a sigma bond. So a sigma bond is when there's this direct sort of end-to-end overlap between two orbitals. You can also get that not between s orbitals but also between p orbitals or d orbitals. So imagine there's the orbital on one atom, here's a p orbital on another atom like that, and they overlap right here, and so the line that contains the nuclei of the atoms, the bond axis is right there. I just sketched that in. And so this overlap is shish kebabbed or skewered by that bond axis. And so we call that, again, a sigma bond. So that's a sigma bond. There's another kind of bond that we call pi bonds, a pi symmetry. So that's where the overlap region is above and below the bond axis. And so this is more side-to-side overlap. So where might you see that is in p orbitals. So imagine I've got an atom here, A, and it has a p orbital on it, so I'll draw a p orbital. Remember, p orbitals look like these balloons, these dumbbells on either side. And here's another atom, and it's also got a p orbital on either side. So if we bring these guys close enough, these p orbitals can overlap on their top and bottom sections. Now the bond axis is going to be here, the line connecting the two atoms, but where is the overlap region? It's not here, shish kebabbed by that bond axis. It's above and below, or to either side of the bond axis. Whenever you see that, where you've got overlap side to side, we call that a pi bond, given by the lowercase Greek letter pi. So this is a pi bond, where you have side to side overlap. Okay, so often we can talk about bond strength relative to symmetry. So due to the better overlap, so you can see that this end-to-end overlap, you can get a better degree of overlap. The percentage of overlap between these two might be higher. And so that typically means that sigma bonds are somewhat stronger than pi bonds. Now you might guess that pi bonds, because they overlap in two places, would be stronger, but notice how this kind of side-to-side overlap, these balloons maybe barely touch each other, so there's not a significant degree of overlap. So typically these pi bonds are going to be a little bit weaker than a sigma bond. So now we're going to look at some of the bonds in some molecules. So we're going to look at ethane. So ethane would have this Lewis dot structure, C single bond C, and then each carbon is then connected to 3 hydrogen atoms. So I'll just sketch those in. Oftentimes an organic chemist will write this formula to kind of emulate the structure. And so an organic chemist might write the formula instead of saying C2H6, an organic chemist might write this structure as CH3CH3. And so that kind of looks like, here's a CH3 group, so we're going to write that down, and it's connected to another CH3 group, so we'll write that down. So this formula tells you a little bit more about the shape of the molecule than something like C2H6 does. So looking at this central carbon right here, we see that there are 1, 2, 3, 4 regions of electron density around that carbon, and we know from VSEPR theory that that gives us a tetrahedral geometry. So here's a picture of that tetrahedron, right? So these two axes, this bond right here, this single bond to this hydrogen and this single bond to the carbon, that's in the plane of my screen right here. This hydrogen is tilted back away, so it's receding into the distance, and this wedge is pointing out, so this one is tilted towards you. So that's the three-dimensional shape, and then the angle right here is that tetrahedral bond angle of 109.5 degrees. So we know from thinking about hybrid orbitals that we look at a central atom and we ask what kind of hybrid orbital would a central atom like this need? Well, when it's got 4 bonding regions around it, we use our table that we learned about in class. 4 regions means that this carbon is going to use an sp3 hybrid atomic orbital. And so that's what's pictured up here in this picture. So this carbon atom has 4 sp3 hybrid orbitals. Each one can overlap with an orbital on another atom. So this carbon and this carbon are going to overlap their sp3 hybrid orbitals, and this overlap right here is on the line connecting these two carbon atoms, and so it is a sigma bond. Similarly, up here, the overlap region between this hydrogen 1s orbital and the sp3 orbital on this carbon, well, that's on the line containing these atoms. So there's a line, a bond axis between this carbon and that hydrogen, runs right through the middle, which shish kebabs the overlap region. So this is also a sigma bond up here. Right? So if we were to count them all, this molecule would have 1, 2, 3, 4, 5, 6, 7 sigma bonds, all total. So those are the bond types. Here's another picture of the molecule made with a sort of ball and stick model. And then these are called van der Waals surfaces that are sketched over the top right here. So these van der Waals surfaces are sketched over the top. And then they've been shaded in a little bit to indicate the charge. So these hydrogens are ever so slightly electropositive, and so that's showing you that these hydrogens are a little bit more positive than the carbons here in the middle, which are a little bit more negative. So there's a buildup of electron density here between the atoms, making them a little bit negative. But overall, this molecule, because of the symmetry and the small difference in electronegativity, would be nonpolar. So that just connects with some other ideas we've been talking about recently in class. Now let's look at a molecule that has a double bond. So this is ethylene, C2H2. So the Lewis dot structure would, look like 2 double bonds, a carbon, and the hydrogens coming off like this. So using our VSEPR theory, we would look at one of these central hydrocarbons, one of these central atoms, and we'd count the number of regions around it. We'd say there's 1, 2, 3 regions around this carbon. So the geometry around that carbon would be, that's right, if you said trigonal planar, you were right. So trigonal planar. And the same thing for this carbon atom, because it also has 1, 2, 3 regions around it. So this whole molecule then would be planar. So let's think about the bonding then. So we've got 3 regions around one of these carbons. So according to our table, we know that this carbon is going to use an sp2 hybrid orbital. Remember, the sp2 hybrid orbitals are made up of 3 lobes. Well, I take that back. Each of the sp2 hybrid orbitals is 1 lobe. So there's 1 lobe. And remember, it's going to have a small one on this side too that we usually don't sketch in. So each one of these is an orbital that this carbon can use for bonding. And we see very clearly that if this carbon atom has these 3 orbitals, that this orbital can be used to bond with the hydrogen down here. And let's say this orbital right here can be used to bond with the hydrogen that's tilting back in the plane. And this orbital right here could be used to bond with the sp2 hybrid orbital on the other carbon. Now, we need to think a little bit about the electronic structure of carbon. So carbon has a 2s orbital in the plain old atom and 2p orbitals. And our normal model, we put the 2 electrons here, and then it's got 4 valence electrons total, so the next 2 electrons go in these empty 2p orbitals right there. So that would be our electron configuration. So what we're going to do in this case to make this sp2 hybrid orbital and be able to make our 1, 2, 3, 4 bonds to carbon is we're going to take this electron right here, we're going to promote it up so it gets promoted, and we're going to take these, we're just going to take the s and 2 of the p's to make a hybrid orbital. So now when we hybridize them, we get 3 sp2 hybrid orbitals, each one with a lone electron in it that we can use for bonding. And then we've also got this unhybridized 2p orbital that's right here with an unpaired electron in it. So what's that going to look like? All right, so up here, let's look at our diagram. So this shows the 3 lobes. So on this carbon atom right here that's in the middle, let me circle it so you know which one I'm talking about, this guy right here. So it has these 3 sp2 hybrid orbital lobes. They make a triangle shape, and this triangle shape is coming out of the plane of the screen at you. So this one is coming out at you, this one's back behind the screen, and this one is in the plane of the screen. So what we can do is overlap this sp2 hybrid orbital with the sp2 hybrid orbital on this neighboring carbon right there. So that overlap is on the line connecting these 2 axes, so that's a sigma bond. Similarly, this lobe that's tilted back behind the plane of the board, that might be to this hydrogen back here, that sp2 hybrid orbital will overlap with a 1s orbital on the hydrogen, and again that orbital is on the line, skewered by the line between the carbon atom and the hydrogen atom. So that is also a sigma bond. Now let's look at what else we have on this carbon. This carbon also has an unhybridized 2p orbital. So remember, the 2p orbital has 2 lobes, so the electron can be up here or up here, move around between those 2 lobes. This is just the probability where you're likely to find those electrons. And so that orbital is this guy right down here. I'm circling it. Right? And it has an unpaired electron in it. So that one unpaired electron is buzzing around somewhere in these lobes. The right-hand carbon has the same situation going on. Another 2p orbital with a lone electron in it. So that lone electron, there it is, and this lone electron that's over here, let's draw it a different spin, they can overlap side to side to form our 4th bond. And so this bond, where the overlap is above and below, or side to side, on that bond axis, this is called a pi bond. All right, so this double bond right here that we see in the Lewis structure, valence bond theory tells us those 2 bonds are 2 different kinds of bonds. There's a sigma bond and a pi bond. So when we blend this together, here's another picture showing us above and below the plane of this molecule, there are these 2 lobes that make up 1 pi bond. Now it's tricky. You might think, oh, here's 1 pi bond, here's another pi bond. No, this is just 1 orbital overlapping side to side with another orbital, and that's just 1 bond. It just so happens that that 1 bond has 2 regions of overlap in the molecule, but it is still just 1 bond, 1 pi bond. Here again is the ball and stick model, and these van der Waals surfaces are showing you where the electron clouds would approximately be, and then they've drawn these colors to indicate something about charge. So the hydrogens again are a little bit positive, and then there's a bigger buildup of electron density here in the middle due to this pi bond. So this end is a little bit negative right here. But again, overall, the negatives and positives all cancel out, and this molecule is nonpolar overall. All right, so this brings us to an important point. A single bond, then, we saw in our last slide, is just made up of a sigma bond, 1 sigma bond. Now it looks like a double bond is made up of 1 sigma bond plus 1 pi bond. And that is always going to be true, that when we have a double bond, one side of the double bond will be a sigma bond and one will be a pi bond. So we use the overlapping hybrid orbitals to make the sigma bond, and the unhybridized p orbital, up here, so I'll write unhybridized because that's an important point. That unhybridized p orbital is then used to make our pi bonds. So let's look at one more case. This is acetylene, and so acetylene has this Lewis dot structure down here, and we know from VSEPR that we have two regions around our central atoms right here. And so around this atom, we have linear geometry with a 180-degree bond angle, and the same thing for this carbon with two regions around it, 180 degrees for this bond angle, and a linear structure between these three atoms. So the molecule overall is linear. So using our table from a few classes ago, we know that when there are two regions, that we're going to use an sp hybrid orbital. So let's again think about our carbon atom and its electron configuration. So here's our 2s with 2 electrons. Here's our 2p with also 2 electrons. And so we need to make 4 bonds with the carbon again, so we're going to promote an electron just up to there. And then we're going to hybridize one s and one p this time to make the sp hybrid orbitals. And when we're done with all the mixing and mashing up, we have the 2p orbitals that are a little bit higher in energy, and 2 sp orbitals, hybrid orbitals, that are a little bit lower in energy, like that. So these sp hybrid orbitals, you remember, have this lobe shape. So there's one big lobe, and then there's a small lobe over here that we usually don't draw. And then there's another lobe here, each with an unpaired electron in them. And so the hydrogen can come up here with its lone electron, and you can get overlap here. And the same thing with a hydrogen atom on the left-hand side with its 1s orbital and an electron. And you can get overlap between those two guys. Now you've made bonds that are skewered by the bond axis, and so these bonds would be your sigma bonds. So there's a sigma bond there and a sigma bond there between the sp hybrid orbital on the left-hand side and right-hand side with the 1s atomic orbitals on these hydrogens, and then we've made these bonds. So remember, though, that the carbon atom also has these unhybridized p orbitals right here, these two p's. So there's one here. You know what? I forgot my other carbon. I'm sorry about that. So get rid of that hydrogen. So it's right on this side. So we need to bring up another carbon over here with, I'll draw it up here, with its sp hybrid orbital, right? And so it's going to have an electron there, an electron in the other sp hybrid orbital, just like we pictured here, 2 boxes, 1 orbital each. And this guy's also going to have unhybridized p orbitals on it. So there's one. There we go. And you can see it more clearly on this picture, maybe. So right here, this little balloon shape that I'm trying to trace out with my pen here. All right, those show you then the sp hybrid orbitals on these carbons. And so you get these end-to-end overlap. Those make the sigma bonds. And then there are these unhybridized p orbitals. So I'll sketch those out right here. So there's one of the p orbitals. And then there's another p orbital that's harder to see because it's coming out of the plane of the blackboard at you. The plane of the blackboard, the plane of the screen. And there's another p orbital back here that's perpendicular. So this one is perpendicular to the plane of the screen. And this p orbital right here that runs through the middle of the molecule, indicated by this dashed line that I just sketched in here, that one right there is in the plane. Okay? So over here on this carbon atom, we also have another p orbital that goes up and down. And that orbital can overlap side to side with the orbital on this carbon. So that makes a pi bond. Similarly, the orbital that's going front back here, coming out of the front and going back behind, can overlap with the other p orbital on this carbon that goes front to back, and that makes a second pi bond. So there's a second degree of overlap right here. That's a side-to-side overlap, so we call that a pi bond. So this triple bond then is made out of, it says 2 lobes of one pi bond, top bottom, and 2 lobes of the other pi bond, front back. All right, so there's the front back, and there's the top bottom. So those make 2 pi bonds. And that makes up our triple bond. So our triple bond is 1 sigma and 2 pi. So we can add one more term to our list here, that a triple bond is made up of 1 sigma bond plus 2 pi bonds. So if we were counting the total number of sigma bonds in this molecule, there would be 1, 2, 3, plus 2 pi bonds. So there's an important consequence of pi bonding in molecules, and that has to do with restricted rotation. So let's look at this molecule. This is what we call 1,2-dichloroethene. Technically it would be cis 1,2-dichloroethane. And so that's the way we name this molecule, to remind people that the chlorines happen to be on one side of the double bond. And here's a picture, a valence bonding picture of what this molecule might look like. So the carbon again has 3 groups around it, so that's going to use an sp2 hybrid orbital, and then it's got an unhybridized p orbital that can be used for pi bonding there. So there's a sigma bond here between the 2 carbons. That's one of our bonds. So one of our bonds has to be a sigma bond, and our other bond has to be a pi bond. And so that's this top-bottom bond. So in this case, the 2 chlorine atoms are tilted out of the plane of the screen at you, coming out at you, and they're on one side of the molecule. So if we could move this group and spin this end like a propeller, we could move this chlorine in the place of this hydrogen, and this hydrogen would then spin down and take the place of this chlorine. So imagine this little V shape right here spinning around like the blades of a propeller. Well, in order to do that, you see what has to happen. So the sigma bond right here doesn't really care, because if I were to spin these 2 lobes inside each other, they still overlap exactly the same. But in order to spin this chlorine and move it up over here where this hydrogen is, and move the hydrogen in the place of the chlorine, I'll have to sever this pi bond right here, because there's no way I can have this side-to-side overlap and spin this side, because this p orbital that's right here, this balloon shape, is going to tilt as I start spinning this group around right here. This p orbital is going to come unattached and spin around, and that's going to break this pi bond. So I can do that, I just have to put in energy to do that. And normally at room temperature there's not enough energy to cause that bond to spin around. And so we say that there's restricted rotation around this bond. There's not enough energy to spin these 2 ends like a propeller. And so that means that this molecule right here cannot spin itself around to become this molecule right here. So this would be trans 1,2-dichloroethene. You don't need to know how to name these. I'm just telling you what the names are. So in this case, the chlorines are on opposite side of the carbon-carbon double bond. So one is in the back and one is in the front. And so we can't spin this molecule around to look like this one without breaking this pi bond. And so these 2 molecules then are separate structures. And in fact, they have different properties, different boiling points, different melting points, and other properties associated with these molecules. One of them being nonpolar, this one over here, and this one over here being polar. The other thing that pi bonding electrons lets us do is think about delocalization of the electrons. So in the case of benzene, so this is a benzene ring, and benzene would have this structure. And so you remember that we drew this in class. So I'm not going to draw all the hydrogens on here, but we know that each carbon is also connected to a hydrogen. So I'm just going to draw a stick, and you'll imagine in your head that I've put a hydrogen on the end here. So this is one of the 2 resonance forms that we can draw for benzene. So the other resonance form will simply have these double bonds moved to different places, right? So I can just move these double bonds around, and that's my other resonance form. So the Lewis structure, then, we say, is a blending of these. Now if I were thinking about how this molecule might bond in the valence bond theory picture, then this carbon right here has 3 regions around it. So that carbon is going to use an sp2 hybrid orbital. That means that there's a p orbital left over that's unhybridized. And that's what's shown here on this carbon atom by this blue, by this lobes, these 2 lobes that I'm drawing in here. So this is the unhybridized p orbital. And so it can overlap side to side with not just the p orbital on this carbon, but with the p orbital on this carbon. And in fact, you get side to side overlap all the way around this molecule. So there's overlap on the top and the bottom. And so that makes a series of pi bonds across this whole molecule. And the electrons that are being shared here are not restricted to being just in this space, like this picture indicates, but are free really to move around. And that's what our resonance picture is telling us, that the electrons that are part of this pi bond don't have to be just localized right here. And in fact, they are delocalized. So D means not. So the electrons don't have to stay just in this area, but in fact are able to move all the way around any which way they want up around this ring. And they could even go down below too. So the electrons we say are delocalized, these pi electrons are delocalized around the bond. The sigma bonding electrons, however, are not. They are fixed in this region of space between these two molecules. Ozone has a similar thing going on in its bonding, so it also has unhybridized p's between the oxygens, and the electrons are delocalized then across this structure. So they're not having to be right in between these two atoms. They can smear themselves out. And it turns out that that smearing out of the electrons helps to build a little bit of extra stability in these molecules, particularly in a molecule like this. And when you take organic chemistry, you're going to learn about compounds that have the property of being aromatic. And aromatic compounds have this electron delocalization as one of their characteristics.